Okay, now we're going to explore a different application of the hydrostatic equation that is useful, and that is buoyancy. So whenever we have a submerged object, there is a buoyant force on it due to the displaced fluid. What keeps boats floating, right? And we're going to develop a model for estimating this buoyant force on an object. So the first question we have is, which model can we use to relate weight of an object and pressures on an object? And really what this should read is forces on an object. Forces on an object. And that is, of course, the mascot of mechanical engineering, which is sum of the forces equal to mass times acceleration. And again, fluid statics, so acceleration is equal to 0, which is great news. If we're using sum of the forces is equal to mass times acceleration, then we need to have a free body diagram, which conveniently we've started over here on the left. In this case, we know that there is going to be a pressure acting on a surface. And remember, a pressure, when it acts on a surface, always acts inward on it, right? From the liquid to the object. So on the bottom, it's pretty obvious what that pressure is going to be. It's going to be a uniform distribution of pressure. And we know how to calculate that pressure because that pressure is just equal to rho GH, right? Let's go here. So P is equal to rho GH, delta P is equal to delta H. So we'll call this equation 1 and this equation 2. It's a little bit more complicated on the sides of this floating box here. On the sides, right, the pressure, at least gauge pressure, is 0 at the surface of the water, right? It's atmospheric pressure, which gauge pressure, remember, is atmospheric pressure minus atmospheric pressure. Sorry, gauge pressure is whatever pressure we're at minus atmospheric pressure. So if we're at atmospheric pressure minus atmospheric pressure, it's 0. So we're at 0 essentially here at the surface of the water. And at the bottom, we know we're at the same pressure as the bottom of the box because at this corner, the pressure is the same everywhere. And we know it varies linearly with height. So what we have is a triangle. It looks like this. This is what the distribution of pressure on that surface looks like on both sides. Cool. So the last thing we need to add to our free body diagram is the weight of the object, which is just mass times gravity, right? So if we go now and go look in the y direction for our sum of our forces. So we sum all the forces in the y direction is equal to, we have negative mg here. Oh, I'm so bad at this. We needed to add in a coordinate system. X and y, there we go. So we have negative mg, and then we also have the pressure here on the bottom, which is going to be equal to plus, we're going to just say pressure P, call that P, times our area, which is A times B, which is our distance into the page, right? B is our distance into the page. And I didn't exactly label this equation very well. So let's relabel this equation. This equation is actually 1 into 3. So now if we take 3 plus 2 and go into 4, we're going to say that, and this is all equal to 0. 0 is equal to negative mg plus pressure. Our equation for our pressure then is rho gh. So instead of P, we're going to have rho gh AB. Cool. And then we're done basically, right? We end up with mg is equal to rho g, and then this is actually the volume submerged of the object. volume submerged. So we're going to say that right here, volume submerged. And mg is actually the F buoyant force. Buoyant force, yeah. Yeah, so pretty simple. The buoyant force on an object, which in this case, since our object's not accelerating, is equal to its weight, is equal to rho g times the volume submerged to that object. So that seems really easy, and it is really easy for a rectangle. So the question you should always be asking yourself is, what is the hard part about this? What is the hard part about this? So here it is when you start asking engineering questions like, where does the force act on the body, right? So we know there's a buoyant force, and we know, I think it's from statics, really, is where you learn this, that the force has to act through a point on a body, because that's how you determine what moments are on it and if it's going to rotate and whatnot. So where does the force act on the body? And in this case, the answer is through the centroid of the submerged section. The centroid of the submerged section. So with a rectangle like this, the submerged section is going to be this green area here that I'm coloring in a little bit. And the centroid of that green section is going to be right here. Centroid. So that's where the buoyant force acts, and the buoyant force acts up from that point. Okay? It gets obviously much more complicated when you have non-rectangular shapes, right? Cool. So why is this important? Why is where the force acts so important? And the answer is stability. Stability, right? I kind of tried to hint at this when I talked about moments and rotating objects and things like that. We need to keep boats pointing the right way up, right? And in order to do that, we need our buoyant force to not try to rotate our boat so that the open part is facing down, right? Let's look what that looks like here when we have two objects. The important part to remember is that we have essentially two forces acting on a boat. It's more when the boat's moving, but this is fluid statics, right? So we have weight and we have buoyant force. And those two forces are going to form a force couple that either acts to oppose or encourage rotation. And let's look at two objects here that are will serve as our examples of stable and non-stable. And by the way, a stable object has a force couple that opposes rotation, and a non-stable object has a force couple that encourages rotation. So on the left-hand side, let's draw in our weight. Our weight, we're assuming these are homogeneous objects. The weight's going to act through the centroid of the object pointed down. So this is mg here. And then our submerged part of our object is going to look like this. There's our submerged part of our object. And if we remember from statics, calculating the centroid of a, this is why we use rectangles, because it's relatively easy. We can break this into two different parts, one rectangle that goes like this and one triangle. The rectangle will have a centroid in its middle, and the triangle has a centroid 2/3 of the way down towards its thick side for both directions. So its centroid is somewhere right about here. Combined, if we're just kind of doing an averaging in our head, the centroid for our submerged section is going to be right about there. So we have a F buoyant going right there. And if we look at these two force couples, they're trying to rotate our object in this direction. So our box has been pushed down and rotated this way a little bit, and the force couple from the buoyant force and the weight of the object tries to rotate it back up. Therefore, it is stable. On the right-hand side here, though, we have a tall, thin object that has been pushed slightly in this direction. And if we do the same exercise we did before, and by the way, this is a great time for you to pause the video and try to fill this in before I do. Try to draw where you think the buoyant force will be and where you think the weight will act through on the object. Assuming, again, it's a homogeneous, uniform object. Cool, I'm gonna assume you paused it and you're back. So if we draw a line down, this is mg, that's pretty easy. That's the weight acting through the centroid. Now the centroid for the submerged section, though, is going to be, we can draw again two rectangles and a rectangle and a triangle. The triangle isn't going to matter much. The rectangle will, and the buoyant force is going to act from the center of the rectangle. Essentially, the triangle doesn't affect it a whole lot, and it's going to act up here. And these two forces are now going to create a force couple, which is trying to encourage rotation in this direction, which is the same direction that caused the perturbation that started this thing rotating initially, right? This is why you could never float a stick straight up and down in water without adding a weight to the bottom. If you add a weight to the bottom, it shifts this mg, the weight force, down to the other side of the buoyant force and creates a stable couple that will try to rotate it the other way. So yeah, stable versus not stable. The first thing you do when you're designing a boat, make sure it's stable, right? Because we want it to be self-correcting. If a wave comes that starts it rotating, it's not going to continue rotating on the other side. A lot of tragic maritime accidents, like you'll see ferries tipping over. A couple things happen that cause that to happen. One is the ferry is overloaded. So if you put too many cars up at the top of a ferry, let's do it in, I don't know what color this is, chartreuse, who knows. We put a bunch of ferries on the top, sorry, a bunch of cars on the top of the ferry. It's going to shift your center of mass upward, which can, for a large rotation, move the center of mass over to the other side of the buoyant force, causing the force couple to change the direction of rotation and cause the ferry to tip over. So, right, something might be stable for small amounts of perturbation, small amounts of rotation. It might try to self-correct, and then if you rotate it too far, that force couple will flip and cause it to completely flip over. The other thing that can happen is sometimes it takes on a little too more water than was expected. So all of these boats have bilges that are purging the water that leaks in constantly, and sometimes the water will cause a bunch of water at the bottom, which the water can actually move, right? So if the boat tilts a little bit, the water will slosh, run off to the side here, creating more mass on the right-hand side and shifting our center of mass in that direction, again, causing instability to a large rotation. So a lot of these boats can work fine, even if they're being loaded incorrectly and have, water leaking into them more than they expect, until a large wave comes, or until somebody accidentally perhaps loads too many cars on one side and not on the other, which will do the exact same thing. So stability is a very important thing for objects on water that are intended to float, even submerged objects, right? You want your submarine to be pointing up and down instead of just rotating freely. Great, so in class, we will do another quiz, not quiz, where we talk about a new design for a life vest. We're gonna answer questions like, you're gonna talk about which of these designs is better, the old school life vest or the new school life vest, and by referencing things like the center of buoyancy, stability, and what is asked for when you're designing a life vest. What is the goal of a life vest, right? Cool, so that'll be our quiz, not quiz for class. And then in the next video, we will do a example problem where we have a box floating in water, held in place by a spring, and we want to know how far the spring is stretching to hold it in place. Cool, which is kind of a model for a buoy, right? Kind of a model for, or kind of a simplified buoy. Great.